Welcome back all. Today we will learn about Slater's rule. Slater's rule was given by John S. Slater in 1930s. The method was used to calculate the effective nuclear charge of an atom. Here the Z star represent effective nuclear charge, Z represent atomic number and sigma represent screening constant. Here we have two shells, both belong to same atom. One is for d and f orbital, another is for s and p orbital. If we start to number them, then it becomes n, n minus 1, n minus 2 and n minus 3. And if this shell or orbital is more, then it will be increasing in size and the number of atoms orbitals will also increase. Same in the case of d and f orbital. n, n minus 1, n minus 2 and n minus 3. We can see that the value for the shielding constant differs in d and f orbital and s and p orbital. In the case of s and p orbital, it goes like 0.35. For n minus 1 it becomes 0.85, and for rest n minus 2, n minus 3 and so on, it becomes 1. In case of d and f orbital, the first case will be same as of s and p orbital. N becomes 0.35. For n minus 1, the value changes. Here it was 0.85. Here it remains 1, and the values remain same for the rest of the cases. Here I have plotted the table as I have explained earlier. We can see for S and P case, the value of n becomes 0.35. For n minus 1, the value becomes 0.85, and for n minus 2, n minus 3, etc., the values remains 1. In case of d and f orbital, the value of n becomes 0.35, n minus 1, 1 only, and n minus 2, n minus 3, the value remains the same. We should also note that for 1s orbital, the value will be 0.30. It should be noted. It means n becomes 0.30 only if the orbitals are present in 1s shell. Now let's solve some problems. Let's calculate the shielding effect for boron. B. The atomic number becomes 5 and the electronic configuration 1s2, 2s2, 2p1. We have to calculate the shielding effect for boron. When we will write in this in Slater's form, it becomes 1s2 bracket 2s2 comma 2p1. Here the we take 1 for p orbital, n minus 2, that is the outermost orbital, we take 1 and we multiply it by 0 because the this atom is shielding the other atoms, so it does not take part in it, so it becomes 0 plus the rest 2 into what is for n minus 1, 0.85, and again we multiply by 2, and for nth shell it is 1. It becomes 0.35. It becomes 2.40. And effective nuclear charge becomes atomic number minus screening constant. So it becomes 5 minus 2.40. Now let's calculate for d orbital. Let's take an example of titanium. The atomic number is 22. The electronic configuration will be 1s2, 2s2, 2p6, and it will go for 3s2, 3p6, and the electron will go to 3d, 2, and 4s2. Now we will arrange it in Slater's format. 1s2 bracket, 2s2, 2p6, 3s2, 3p6, 3d2, 4s2. Here the 4s2 has no significance here, so we will not take this. We will calculate for this one. So the sigma becomes 1 into the only one electron will be considered, the another will be taken for shielding, so it becomes 1 into 0.35 plus rest, as I have told earlier, the value will be for 1 for each of the atom. So we will calculate the rest of it. 6 plus 2 8, 8 plus 6 14, 14 plus 2 16, 16 plus 2 18. It becomes 18, and it becomes 18.35, and the effective nuclear charge will be Z minus sigma. It becomes 22 minus 18.35. Effective nuclear charge will be 3.65. If you like this video, don't share to like, share and subscribe. Thank you.